Okay, my name is Cameron Hopkins. I'm from Western University. I'm in my 4th year of my honors physics degree. I did some research this past summer supervised by Dr. Shantanu Basu in the Department of Physics Astronomy there. And I'll be talking about a novel theory for the formation of brown dwarfs, more specifically three-body simulations and circumstellar disks. I feel like this talk doesn't really belong here because we're talking about galaxies and the universe, and I'm going to go to the smallest stellar objects. So, first things first, what's a circumstellar disk? I think these pictures kind of describe it adequately enough. You've got a thin disk of dust. It's thin and in a plane because there's angular momentum in the system and that flattens it out. And in the center there's a bulge where most of the matter is collecting. But a key thing to note is that little objects can form, little clumps can form in the dust. You can see on the right image there's a couple bright spots in the dust. Those are likely planetesimals in that image. But we're going to talk about clumps that are a little bigger than that. Before we get to that, what exactly is a brown dwarf? Well, it's a low-mass stellar object, too low to fuse hydrogen, and it's in the about 13 to 80 Jupiter mass range. There's a bunch of different formation mechanisms with these stellar objects. If we're below 13 Jupiter mass, we have core accretion and the accumulation of planetesimals. That would be like in that right image on the previous slide. And those would form just planets in a typical solar system. If we go any greater than 80 Jupiter mass, we get direct collapse of the dust cloud and we form a typical star. Now that was the understanding of how brown dwarfs formed, but it doesn't quite explain it properly less than 80 Jupiter mass. And we're going to talk about that region where there's immense gravitational instability in the rotating disk. And we can have these clumps form that either get fragmented by the immense gravitational force and their matter spewed out and redistributed throughout the system, or it holds its form and it gets ejected from the system. And those ejections are exactly what we want to look at. Here's a summary of brown dwarf properties. Their mass, between 10 and 80 Jupiter mass. It's a bit of a fuzzy line between both ends. Key point, too low for fusion to occur. That's why they're so small and cold. There's no fusion. The radius, about Jupiter mass or smaller because the greater mass and there's no fusion to sustain the size of it, then it will collapse a little more. So that's why it'd be smaller. Temperature about 600 to 2200 Kelvin, but you can also find objects that are smaller than that temperature, or less hot rather. For comparison, the Jupiter temperature there is 200. So, my supervisor, Dr. Basu, and his colleague, Ed Robiov, quite recently, actually just over the summer, published a paper on a novel theory for the formation of brown dwarfs and very low mass stars. And this is a figure that was chosen from it. He ran some numerical hydrodynamic simulations where he basically took a mass for the dust cloud and he gave it some angular momentum to let run. And you can see these little clumps that form, which will come down, like right there and there. They behave like I mentioned before. They can either fragment or redistribute their mass, as you can see sort of in this area, and all the mass is being spewed out around. Or they can form a tight clump, like where that arrow is pointing, and be ejected from the system. And we're going to blow that image up there. You can see where the arrow is pointing, it gets thrown from the system. And that clump takes away much of the mass from the central disk. And one thing to keep in mind here when I show the next slide, the mass range of those clumps is about 80 to 350 Jupiter mass, but that's the mass of the clump itself, not the final object that it forms. The process of cloud collapse is not 100% efficient, and you might actually get a third to a half of the mass of that clump actually results in the final object. So that's well within the brown dwarf range. Their ejection velocity from the disk, 0.8 kilometers per second, probably doesn't mean anything to you, that number, but it's several times greater than the escape velocity required for a clump in that system with that mass. And on the relative scale, I read a paper recently that was showing stars with velocities upwards of 100 kilometers per second, so that's actually fairly taken on the scale. The time to ejection from when he hit start to when the object was thrown, about 180 to 700,000 years. Now, the project that I worked on was a little simpler. We didn't do a numerical hydrodynamic simulation. We just took some simple M-body code developed by a group of researchers at the University of Maryland, and I added a time and position-dependent mass accretion step to the code. What does that mean? It means that depending on where the clump is in the system, it'll be gaining mass according to a profile for the disk density. And that profile was based on a power law. And this was theoretically developed by Lynn and Pringle in 1986. But not only is it theoretically valid, but it's also what we observed. We observed power law disk distribution for the density of -3/2, and it looks something like this in log space. This is actually the model that I use in my code. From 0 to 3 astronomical units, it's constant 10 to the -7. Between 3 and 300 astronomical units, it decays in that power law. And any greater than 300 astronomical units, and there's no mass accretion, so it's 0. And this causes some pretty interesting stuff to the dynamics of the system. It adds an extra level of chaotic behavior. And you probably know that n-body simulations of Newtonian gravity is inherently chaotic as it is. This just adds another step to that. So we chose a central mass. Remember when I showed you the circumstellar disk, there's a central clump. We gave it 0.1 solar mass, and we let it evolve at 10 to the -6 solar mass per year, and that was constant. And then we chose 2 clumps, mass chosen randomly from a Gaussian distribution centered at 10 Jupiter mass with a standard deviation of 0.2. That gives us a fair distribution of masses to play with. And their starting positions were chosen from a random distribution between 1 and 10 astronomical units from the central clump. And then we gave them initial velocity such that if they were isolated, nothing going on, it would be in a circular orbit. So I have a simulation to show you. It's not too exciting, but